Good day, guys. Nice having you guys once again. Welcome to Exquisite Tutorials, and let's do some Rhemas. It's Chem 101. Chem 101, and today we'll be looking straight into some Rhema questions, and we're using it to explain everything you should expect in your exam hall for your Chemistry 101 exam. I need you to be fast with this, and I know it's going to help you by God's grace. Trust me. Okay, first of all, let's look into something. Let's look into thermodynamics. I'm going to give you a brief illustration of what you should expect from thermodynamics. Now, what is thermodynamics? Thermodynamics talks about heat and everything, heat change, and every position or every possible means that a substance or heat can transform from one order to another, this transformation of heat. And we'll have the laws of thermodynamics. We'll have the first law, the second law, and the third law. Most times questions comes out from the first law. Let's talk about the first law of thermodynamics. First law. Now, when we are talking about the first law of thermodynamics, the first law of thermodynamics is actually concerned about heat and energy. Has to do with energy. Now, the first law of thermodynamics makes us to understand that energy can neither be created nor destroyed. Now, how do we explain it? Okay, let's say, for example, we'll have a substance. This is a system. This is a system. Or okay, let's draw something like this. Let's say this is a system. This is a container, and this is the environment. All these ones are the environment. Now, what the first law of thermodynamics is making us to understand that heat can either be transferred from here to this place, from the surrounding to the system. Okay, let's say surrounding to system, or heat can go from the system to the surrounding, which means that when heat is going from the surrounding to the system, it means that here is gaining heat, becoming positive, here is losing heat and becoming negative, which means the heat was not created from nowhere, or energy was not created from nowhere. So energy can neither be created nor destroyed. Energy can only go from one means, from one place to another, or from one means to another. Okay, let's say, for example, for example, let's talk about your electric current in your pressing iron. Now, in your pressing iron, energy is going from the electric current, from current electricity, and is being passed to your pressing iron as a heat. So energy is being transformed from one state to another. Well, whereby, for example, let's say you put your fire, you are using your gas cooker. This is your cylinder. There is fire here. Okay, let's sketch this thing from here. Let's say this is your gas cooker. Don't mind my drawing, just understand what I'm trying to explain. And there's a fire here. Now you are placing a bowl or a pot. What is here is water. Let's say this is water. Now, what thermodynamics is trying to explain is that the heat does not come from nowhere. The heat is coming from your gas cooker. Your gas cooker. So the pot, the heat is transferred from here as your fire to here, your water, to change the state of your water from liquid to probably vapor. So the first law of thermodynamics is making us to understand that energy or heat can neither be created nor destroyed, but can only move from one state to another, or from one substance, or transferred from one substance to another. Now, I want to explain three systems to you. We have three systems. We have an open system. We have an open system. We also have a closed system, and we have an isolated system. Now, I want to explain these three systems to you with a diagram. Let's sketch an open system. Now, this is an open system. This is a closed system. The system is closed, and isolated system. Now, let me explain. An open system is that system which is open, where, just like you say, in an open system, this place is totally open, meaning heat can, okay, here's the system, and here is the surrounding. Don't always forget, here is the surrounding. The surrounding means the environment. If this is the system and this is the surrounding, in an open system, heat can be transferred from the surrounding to the system. Okay, let's say heat. Let's take here as heat. Let's take here as heat. And as well, energy can be transferred. Let's take here as energy. Or let's take work. Energy or work can be done from the surrounding to the system as well, or from the system to the surrounding and vice versa. Now let's go to a closed system. A closed system is that system where energy or work cannot be done on the system because the system is closed already. But heat can be transferred from the surrounding to the system. I don't know if you're getting me. Energy or work cannot be done on the system because the system is closed already. Now, you will believe me that in a system, okay, let's say for example, you put, okay, let's say you are cooking or you are boiling water. Once you have covered your pot with the cover of the pot, you can no longer put in any substance inside the water to increase the mass of the water. You cannot put in beans, you cannot put in anything once you have closed the cover of your pot, which means work cannot be done on a closed system, which means the mass, okay, here, the mass of a closed system is constant. Note this, mass is constant. But here, both mass and heat can be changed because the system is open. Mass is constant, but heat, now, the fact that you have closed the system, that does not mean that heat cannot be transferred, because heat can actually pass through, can actually be transferred through a substance while closed. So the fact that you have closed your pot does not mean that heat can no longer go in. So long your gas is there and the pot is on top of the fire, definitely the water will boil. So that means that heat can be transferred into a closed system. But an isolated system is that system that both mass and heat is constant. Both mass and heat is constant because heat cannot be transferred, neither can work be done on isolated system. Now, let's forget about the systems. Now, let's go back into the internal energy of a system. Now, this is talking about the equation of the first law of thermodynamics. Now, just like I told you to understand that the first law of thermodynamics talks about the internal energy of a substance, talking about heat change. Now, let's say, for example, this is the equation. The equation for first law of thermodynamics or internal energy, you are going to get this. You are going to get an equation like this in your exam hall. Now, this is the equation. delta U is equals to Q plus W. Now, let's explain this. Where delta U stands for internal energy of a system, let's say where U is equals to internal energy of a system, Q is equals to heat, W is equals to work done on a system. Now, just like we explained the three systems, that means for an isolated system, the internal energy is going to be constant because there's no work done and there's no heat transferred. Just like we made us to know that internal energy is equals to quantity of heat plus work done. For a closed system, the internal energy is going to be equals to the heat, because there is no work done on a closed system. But an open system, internal energy has this formula. Now let's explain. Now, when you're talking about there's a difference between this formula. I want to give you a hint for physics students, those writing physics 101, in case you're going to see thermodynamics in your physics exam. In chemistry, this is the formula for internal energy. But when it comes to physics, chemistry, okay, let's say chemistry. But when it comes to physics, for my physics students, internal energy delta U is equals to Q minus W. Now, I will explain to you. Now, the difference why internal energy in chemistry and internal energy in physics is different. Remember, this is a chemistry class. We are focusing on chemistry, but I just want to explain something for you that will meet something different in your physics class. Now, when the difference here is the point of view. When we are studying chemistry, we are studying the point of view of the system, just like I explained to you. Now, this is the system, and this is the surrounding. This is the surrounding. Here, system. Now, when you are studying chemistry, your point of view is the internal energy of the system. But when you are studying physics, chemistry, your point of view is some internal energy of the surrounding physics. Now, when we are talking about point of view, the point we are calculating your heat from. Okay, let's say when you are studying chemistry, your point of view is the internal energy of the water that you are boiling on with your gas cylinder. But when you are talking about physics, your point of view is the internal energy of the gas cylinder or the environment where you are boiling the water. Now, here is the formula for chemistry, add up for physics. Now, let's say, for example, in chemistry, when heat is given out from the system, it means when heat is given out, or when work, let's say for example work here, because here we are talking about it is the sign of work that change for both of them. Here work is positive, here work done is negative. Now in chemistry, when work is done on the system, it means W is positive. Now let's explain. When work is done on the system, because this is actually what happened here. Work is done on the system, here work is done on the system. Here is positive, here is negative. Remember our point of view. Now in chemistry, when work is done on the system, it means that energy is transferred, energy is transferred from the surrounding to system. That is actually when work is done. Work done. This is work done. Energy transfer from the surrounding to the system. Now, since in chemistry, our point of view is on the system, that means the system is gaining energy, so the system is positive. I don't know if you're getting me. It means that you have transferred heat from the surrounding to the water you are boiling. Now the water has gained more heat. So which means W here is positive. Remember, the point of view is the difference. Now same thing happens in physics. But in physics, due to the fact that our point of view is the surrounding, not the system, that means when work is done on the system, energy is leaving the surrounding to the system, so the system is losing energy, so the work done here is negative. That's just the difference, your point of view. Grab that. Now let's proceed further. So since we are talking about chemistry, we are going to be using our equation for chemistry, which says that U is equals to Q plus W. Now let's say, for example, if you are given equation like this, calculate or what is the internal energy of a system if the work done on, remember on the system is work done is 50 joules and energy or heat transferred into the system is let's say 2. That means Q is equals to 2 and W is equals to 50, which means your internal energy, which is change in internal energy, is equals to 2 plus 50, which is equals to 52. And let's say, for example, you are still asked, what is the internal energy of a substance whose work done by the system? Now, let's explain this. When work is done by a system, it means the system is giving out energy to the surrounding. So in chemistry, W will be negative because work done is giving out. Oh, I think we shouldn't remove this structure here because work done is giving out into the surrounding. It means that here is losing, let's say when we are using 50, is using 50 joules of energy to the 50. So here we'll be having minus 50 and the surrounding will be adding plus 50. So what is the okay, let's say, for example, what is the change or in internal energy of a system when the work done by the system is 50 and the heat transferred into the system is 2. Now let's go again. Here it means that change in internal energy, which is equals to Q plus W. Remember, our Q is 2 and here our W is minus 50. 2 minus 50 will give us minus 48. Remember, here is positive 42 because work is done on the system, while here is negative 48 because work is done by the system. I don't know if you understand. It's very clear. And for those writing physics, in physics, if work is done on the system, remember, we are considering the surrounding, not the system. It means work is leaving the surrounding into the system, so the surrounding is negative. But when work is done by the system, it means energy is leaving the system into the surrounding, so the surrounding is positive. But don't be confused here. We are only talking about chemistry. Okay, let's say, can we take one more example? Let's take one more example before we are done with first law of thermodynamics. Okay, let's say for example they said calculate the work done. Now the internal energy of a system is 70 joule. What is the work done if the quantity, what is the work done on the system if the heat applied on the system is 30? Now remember here, well, the internal energy is delta U and the heat is Q. So if delta U is equals to Q plus W, so W will be equals to delta U minus Q. So therefore W equals to, where delta U equals to 70 and Q equals to 30. 30 minus 70 is equals to 40. So it's as simple as that. Now from here, let's move to the second law of thermodynamics. The second law of thermodynamics. Now, when you are talking about the second law of thermodynamics, the second law of thermodynamics talks majorly on entropy. What is entropy? The level of disorderliness. Talks about entropy. Okay, let's say second law talks about entropy, and entropy is given delta X. Now, what is entropy? Entropy is the level of disorderliness of a substance. Now, when we are talking about the second law of thermodynamics, the second law of thermodynamics makes us to understand that a natural system, a naturally spontaneous system has the level of orderliness for a natural, I will explain, spontaneous system is greater than 0, which is to say that a natural system or a natural spontaneous system has a higher level of entropy. Now, how do we explain this? Okay, it is expected, okay, let's say this is heat. We say a body, a conductor, here is heat, here is cold. Naturally, it's expected that heat is going to move from a hot body. Oh, sorry, this is supposed to be hot body. Now we are talking about heat movement. It is naturally expected that heat is going to be moved from a hot body to a cold body spontaneously, without any added energy, anything working on it, because it is expected that the level of disorderliness is high for a natural system. So naturally, heat is expected to move from a hot body to a cold body. Okay, let's say for example, this is a ground. You place a ball here. Okay, now, if this is a body and you place a ball here, it is expected that naturally the ball will move spontaneously from this higher here downwards, because it's expected that the entropy of a natural body is high. So without stress, objects will move spontaneously from a high level to a lower level. That is all you need to understand about the second law of thermodynamics. And one thing you also understand that is that an ideal system, for an ideal system, okay, let's say for an ideal system, entropy is equals to 0, but natural spontaneous system entropy is greater than 0. Okay, this will be all you need to understand on thermodynamics. Stay tuned. From the next video that I'll be doing shortly, we are moving straight into Rhema, all the questions that you are expected to see in your Chem 101 exam and how to solve them. Wait for it. Exquisite. It's coming back right now.